Let's talk about the average value of a function on an interval. So just for a concrete example, we can consider the function f(x) equals x squared on x equals 1 to x equals 4 as pictured in the graph here. So the idea is that f of x equals x squared takes on an infinite amount of values from 1 to when x goes from 1 to 4. What is the average of all those values? Well, normally when you have an average, you add up some numbers and you divide by how many there are. But there's an infinite amount of them in this case. So it's a calculus problem. But as usual, you can break it up into smaller parts and then add them all up and then take the limit as the number of them goes to infinity. So the average value is going to be approximately the sum of f of each of these little subinterval parts up to f of x sub n minus 1, and there are n values there because you have the 0, 1, 2, 3, 4 all the way to x sub n minus 1, and that gives you n values there. So this is correct so far. That's not the actual exact value of the average, but that's an estimate. Then we realize that n equals b minus a over delta x. So we substitute that in, and we convert over to the summation notation, and it starts looking like part of a Riemann sum up there. So then we divide fractions, which means we invert the divisor and multiply. So the delta x comes up here. The b minus a is down there in the denominator. Then we realize that this delta x can be multiplied in to the sum on every one of the f values. It could be factored out, it could be multiplied in. We're going to multiply it in so that the expression will look exactly like the Riemann left sum, which it does here. Now we're going to take find the actual average value of the function, because we're just going to take the limit as n goes to infinity of this expression here. Of course, the b minus a is just a constant, so that factors out. And the top part is the left Riemann sum, and we know where that goes when n goes to infinity. It goes to the definite integral. So here's our formula for the average value right here. Okay, now what's interesting about this is that there's a way to geometrically think about this. The average value can be expressed this way: average value times b minus a. By just taking this b minus a and multiplying it over to the average value, you're going to get this expression. This equals this. Well, that integral is the area pictured here. So what we need is an average value somewhere on this y line. Somewhere here there is an average value that will make the rectangle area of average value times b minus a, because this is b minus a here. Here's your b minus a length. And let's just say you thought that 3 was your average. So then the average value would be, say here, times the b minus a would give you a rectangle area that you were saying is equal to the area under the function. But it doesn't look like it there. This yellow area is a lot bigger than the green rectangle area. Therefore, that's not it. So 3 is out. That's not the answer. Then let's say you thought it was 12. Let's say you thought the average value was 12. The average value times b minus a has to be the area under the curve. So the average value times b minus a is represented by a rectangle. So if you thought it was 12 for the average value, that'd be this rectangle. And you'd be saying that this area is the same as the yellow area. But you can see it's a lot bigger. And why you can see it's a lot bigger is that this part here is a lot bigger than that part there. So it can't possibly be the same. Alright, so let's go to our next slide. Alright, so we don't think that 12 was right. Let's erase that off of there. And let's go on and calculate the actual value on the next slide here. And we see the average value of f of x equals x squared on 1 to 4 is 1 over b minus a, integral from a to b of the function. That's 1/3 times the integral. If you look up the antiderivative of x squared on Wolfram alpha, you'll see that it's x cubed over 3, and you could check that by differentiating x to the third over 3, and I think you can see that you would get x squared, so that would work out. And we have this new notation of evaluating that antiderivative at 1 and 4. We draw this little sort of bracket here. Instead of writing the f of notation, we're going to do x to the third over 3 evaluated at 1 to 4, and that's 1/3. Stick the 4 in because it's f of b minus f of a, so f of b is 64/3. Subtract f of a, which is 1/3. That's 63/3 in there, which is 21. So it comes out 7. So 7 is the number that should be the average. And then when you see this picture, here's your 7 right there, that height, that's your 7. And here's your b minus a, that's 1 and that's 4. So that's 3 across there. And this is 7. So this area is 21. And so the area of the rectangle is 21. And the area under the curve here must then be 21. Which you can see that it's working out because the rectangle is over this amount from the curve, but it's under this amount, and those are looking like they're canceling out. This is looking like it's equal to that. So 7 does really look like the right placement to place the height of that rectangle, so that the rectangle area will really equal the area under the curve.